today is going to be a different kind of lecture, and I don't think I'm going to go for the whole period of time. There's just no way I can be coherent, sensible, and say something really worth listening to for 4 hours, right? So there's no way. So maybe we'll go for 1 hour and something, take a break and see how it goes. And then I think it's really, really unhealthy for you to stay for 4 hours in this room. It's not good for your brains, it's not good for your health. So I think you should just take some time, go out to the beach. You want to think?
Water sports.
Yeah, yeah, water sports. That's right. So today I'm going to well, it's going to be a talk where I think I will probably have to make some random choices as we go along, because I'm not quite sure exactly where I'm going to end up. But I'm going to have my evil Bill, who will be trying to provide technologically advanced devices for me. I don't trust Bill. And Bill, nonetheless, you know, I know this guy for a long time. And well, since when? Yeah, we met you were working for Hewlett Packard at the time in the UK. Yeah, and this guy is like no nonsense guy, you know, just, I remember when I met him, I was, you know, for me, it was all C-star algebra, and for him, you know, screwdriver and saying, no nonsense, you know, here's a random number generator.
And this is as a theorist.
Right. So the scenario I want you to have in mind is, for the purpose of this talk, is that there is Bill, and rumor has it that Bill has advanced quantum technology. And I'm very keen on advanced quantum technology, but I don't entirely trust Bill. We had some history, that was a good one. And I'm going to, but I don't have this technology that he has, and I'm going to purchase a device from him. And this device is supposed to, and Bill claims that, you know, it's going to generate random numbers. Now, it's not only me who doesn't trust Bill. Most people do not trust Bill. So Bill now is a little bit in a problem because he has this startup quantum company now, and he wants to sell those devices, and nobody's putting any trust into this. So then Bill comes with the idea. Bill says, look, guys, you don't have to trust me. You can test yourself that what I'm selling is genuine, that what I'm selling is good. And so therefore, I provide you with a quantum random number generator that has this property that you can test yourself, and you don't have to trust me. So this is the way, and you know, you can easily imagine a situation like this where a certain, you may not trust certain companies, certain governments, certain entities, and nonetheless, if they can provide you with tools that you can verify yourself, then it's fine. And it's almost impossible in the classical world. So this is a kind of a broad scenario. So let me go first to this random number generator that you saw, a kind of random number generator that you saw on the slide. So the beam splitter, right? So the first thing that you can say, well, if you believe in quantum physics, so if you have a single photon source and you have a, say, 50-50 beam splitter, and then you put 2 detectors here, then you know, if you trust quantum physics, and we trust quantum physics, the best physical theory we have, then this will generate completely random. You cannot make a prediction whether the photon will go here or there. You simply cannot. There's just, the nature of quantum theory says that this preparation takes you with equal, well, whether it's equal probability depends on this, but let's don't worry about equal probabilities. We will deal with that later. But suppose it is a Platonic beam splitter, and here we have the probability half that the photon will go here, and the probability half it will end up in this photodetector. So in the first approximation, Bill comes to me, he puts this thing into a box, And then he says, look inside. You know, why don't you trust me? This is a random number generator. Now, I look inside, but you know, I'm not as accomplished in all this engineering as he is. So I see, yeah, there's sort of what looks like a photon source, fine. What looks like a beam splitter, fine. You know, and photodetector. So maybe indeed it works. Maybe. But you know, it is the case. Imagine that he's so clever that this beam splitter is a device that he manages to hide something there. So this photon goes, is absorbed, and he has some kind of a memory stick and sends photon randomly into this and this direction. And he may be so clever in engineering that he knows exactly where the photon will go. So it is random, maybe for me when I look at it, but it's not random for him because he can predict. So he can trick me here. Because of this very sophisticated engineering, he can just build this beam splitter in such a clever way that it doesn't really reflect the photon. It absorbs the photon, and then there's a source of the photons inside the beam splitter, and one photon goes this way, one photon goes that way. How would I know? I wouldn't. So I'm saying to Bill, look, Bill, it looks like a good beam splitter, but I'm not buying this, you know, I'm not so sure because you are so clever. You spend some time with Hewlett-Packard, you spend some time with NTT, so you have all this photonic technology, I'm not buying this. So the Bill said, well, you know, then I have another option for you. So Bill accepts that this may be a little bit too much for me to accept, and then he comes with a device which actually has two parts, and never mind how it is constructed, but so instead of just one box that generates random numbers, so let's consider two boxes that generate random numbers, so like 0, 1, 0, 0, 0, 1, 0, 0, and 1, 0, 0, 1, 0, 1, 0, 1, whatever. So now Bill, and this is actually what this lecture is about, that with the help of two devices that behave in a certain way, because Bill constructs them in the following way. Each device has input that I can choose. Call it X and Y. So those are binary inputs. X is either 0 or 1, so there could be a switch. I can put it in two positions. And the same for Y. Now, each time I just put input, the device generates output. So this comes A, and call this B. And sort of, if I do it repeatedly, the devices will generate sequence of zeros and ones. So now there is a tacit assumption, and we will look at it very carefully later, that I may be choosing my X and Y randomly, but this is going to be my private randomness. You may ask me the question later, why are you going to lose your randomness in order to testify for something which you want to get randomness from, but we will address this question later, okay? So for now, the two devices will allow me to run a certain test on them. So I'm going to be looking at output from one of them, but I will be using the other one for randomness test. So the other one is kind of auxiliary in this scenario, but every now and then I will be checking whether the certain, for example, I will be picking up certain outcomes in pairs, and I will be checking whether a certain condition is satisfied. And when this condition is satisfied, I will be getting more and more and more confident that Bill cannot predict what are the values of those bits here. So this is the broad picture. This is where we are going, okay? So it's amazing that this is possible. and the fact that the Bill will be able to sell the device is equally amazing. We'll be all encouraged to buy devices from him by the end of the lecture. Okay, so let's first, so this is a big picture. Let's go now a little bit into, let's try to be precise of what kind of assumptions are here and so on and so forth. So those devices here, I will assume, and this is a very unrealistic assumption in the adversarial scenario, that each round is independent from the previous one and identical. So we call this IID assumption, so that the devices, every single run is independent from the previous one, and statistically speaking, they are identically distributed. So the devices behave in the same way in each round. So that, of course, is unrealistic. Bill has a technology, has some memory, all those runs may depend on the previous ones, and so on and so forth. So it's perfectly possible. But let's start with a simple case. Let's see what we can do with a simple case. And then I can only comment at the end that there are ways to go beyond IID, but IID is the basic block to which you reduce more complicated scenarios. So let's sort of first talk about randomness and how we measure it. Now, when we just have a source that generates binary digits, zeros and ones, what do we, or do I mean for the purpose talk of the things are random? And of course, you know that volumes are written about this, by the way. If you look, Google or just look up randomness, and there will be lots of definitions. There's a randomness of something defined in terms of Kolmogorov complexity. There's a randomness defined this way. There's randomness defined that way. But for the purpose of this talk, the randomness will be defined as the probability of guessing the bit value. So it's a very simple thing. And if I have a source that generates this bit, the probability of guessing, call it p-guess, is our measure of randomness, kind of. So that tells you if it's half, then, nobody has any clue what's going on. And if you want to be precise, there's going to be probability of X given Bill's knowledge, so PXB. So that's probability of guessing by Bill. My probability of guessing could be half, but he prepares everything, so he could be guessing with a higher probability. So I will just simplify this so let's say PG is probability of guessing. And when I say probability of guessing, I assume that's probability of guessing from Bill's perspective, because he has the best possible knowledge about those devices. So if we do any estimates, we cannot do better than Bill. So therefore, the probability of guessing is conditioned upon Bill. But traditionally, it's more common to take the log of that, so in particular, so minus log to the base 2 of PG, which is min entropy, is the measure of is a sort of a good measure of randomness. It is a good measure of randomness because essentially it can tell you there are procedures that if you have many repetitions that can extract this number of random bits per bit generated. And we'll talk about this in a moment. So you can, if you want to say how random something is, you can say, what is the probability that someone is going to guess it? But you can also say, oh, well, I use mean entropy. The mean entropy is the log to the base 2 if you want to use bits of the probability of guessing. Now, in fact, you know, when we have random sequences or sequences where there is a partial knowledge that or where bits appear with a certain probabilities, there are various techniques, mathematical techniques, that we can use. For example, in this case, if there's a certain bias in the beam splitter or in Bill's sort of way to generate this stuff, we can actually, in a simple way, we can make all those probabilities equal, especially in this, if we operate under IID scenario. So let me just show you maybe one or two tricks how it works. So for example, assume, so this is, just have this in mind. And now we are, let's say that I know that there is a sequence of zeros and ones generated, and I want to have a uniform sequence of zeros and ones. But I know that the, say, device is biased one way. So for example, 0 appears, so let's say from a certain device, it doesn't have to build the device. This one is sort of a somewhat separate example. So it generates 0 or 1. Let's say that 0 appears with probability p and 1 with probability 1 minus p. Then I don't know what the p is. And I get a sequence of zeros and ones. Of course, you know, I can analyze frequencies and find out. But my objective here is to make sure that I have a uniform, that somehow I turn a sequence of zeros and ones into sequence of zeros and ones where zeros and ones appear with the same probability 50%. So how can I do it? So it is like a little bit like you have a biased coin and you don't know how biased it is. And you want to toss this coin and make sort of a fair judgment. So for example, you know, like a referee before the football game, you toss the coin. But this coin is very biased, so clearly it's not good for taking fair decisions. How can you turn this biased coin into unbiased coin? So that's the question. So the first idea, a kind of clever idea that is due to von Neumann. So he said this, okay, have a sequence, so you keep on tossing coin. And he says, have a sequence, for example, 0, whatever. And then von Neumann said, if you have a sequence like this, and you want to have a sequence of zeros and ones, where zeros and ones appear with the same probability, group those things into pairs. So I group them, those bits, into pairs. And he said, okay, for 0, 1, write 0. For 0, 1, write 0. For 1, 1, discard it. For 0, 1, write 0. For 1, 0, write 1. So the basic idea is, if you have a sequence, if you have a pair 0, 1, consider this to be 0. If you have a pair 1, 0, consider this to be 1. If you have 0, 0 or 1, 1, just discard it. And you can see that the relative frequency, right, of this 0 will be p1 minus p. The relative frequency of this is the same, 1 minus p. This will appear with probability p squared, with this with probability y minus p squared. So those are different, but the relative frequencies of those two are identical. So what you have here is that the probability of 0 and 1s generated this way are the same. So you have a uniform strings. The price you pay, of course, is that you discard some of them. So whenever there's 1, 1 or 0, 0, it's not good enough, you throw it away. So that's the first way. So in other words, if you have a coin and you know it's biased, so you keep on tossing it until you get a sequence either 0, 1 or 1, 0, and then you know that those pairs appear with the same frequency. So you can turn a biased coin into unbiased. You just have to simply toss it a few times and make sure that this works. So this is sort of known as a von Neumann trick. But it's a good example of randomness kind of extraction. You have something that is not random because something is more probable than other. So people can guess then, for example, 0 will appear more often than 1. But if you want to sort of like make those probabilities equal, you can use this trick. The price, as I say, the price to pay, you just you drop some of those, you discard some of the data. But there is an improvement, actually quite recent. I don't know when von Neumann came up with these ideas in the 50s or 60s, but there is an improvement due to Perez. I think from the 90s, it's 1992 or so, where he managed to say, well, wait a minute. And it's, it's so simple that even you can do it if I were to challenge you to go and work hard, you would probably come up with a Perez algorithm. So the Perez algorithms say, okay, well, keep those discarded items. And then keep the discarded items. For example, I have 1, 1 here. I have maybe another discarded item somewhere there, 0, 0. And the Perez says, convert 1, 1 to 1, 0, 0 to 0. And you know that this appears with probability p squared, this 1 minus p squared, so they're different. But then run the von Neumann again. So you see that then you have the sequence of discards, and we run von Neumann again. And you can show that this actually, the Perez algorithm is much, much more efficient in extracting the random, or making data uniform. So this is, one thing that we can do. If we are, that's why I'm saying, if the beam splitter is not symmetric, so we don't care, as long as the outcomes are independent. So this assumption is important, though, that the outcomes are independent. We don't even have to know this value of p, right? Bill constructed the beam splitter. Even the best NTT technology is such that, okay, it's not perfect. And I don't care. I say, fine, Bill, I can live with that. Give me not perfect beam splitter. I can still turn it into a perfect beam splitter, because as long as the outcomes are independent, so I can run it a few times and can use, for example, the von Neumann trick to symmetrize it. So that's easy. Another maybe interesting extraction, which is worth maybe showing you. Is this clear, by the way? Okay. I'm going to erase. I like this, your beam splitter. I don't want to erase it. Maybe I'll just write there. So the other interesting idea is due to Shannon, and that shows an interesting use of the Shannon entropy. Oh, by the way, as a homework, you may want to sort of check how efficient is this algorithm. So in terms of how much data we have to discard, at least look at it for the von Neumann. Because there is a price to pay, so we discard some data. So you may want to just calculate for yourself the efficiency of the whole thing. The other thing, which is kind of interesting, which I'm not going to use it, but maybe when Nina gives her talk or someone else talks about asymptotic key rates and the like, you may be using this thing, or maybe you'll have a right intuition. So let me tell you about the randomness in asymptotic limit. So when you have again a source which generates 0 with certain probability p and 1 with probability 1 minus p, and it generates many of those sequences. So you have like huge number n. We are still working on the IID assumption, right? Then if you have a huge block of n binary strings, So you may just wonder how many of them you have. Well, the answer is simple. You have 2 to the n of them. Okay. But if they are biased, so if each bit is generated with probability p, if each 0 is generated with probability p and 1 with probability 1 minus p, then we have an interesting situation where we have typical sequences by the law of large numbers. You know that in a sequence, in a typical sequence, you will have p times n zeros and 1 minus p times n ones, right? And we know that the likelihood, the probability that you are not having a typical sequence gets increasingly smaller and smaller and smaller when you increase n. So in this whole set here, you have a set of what is called typical sequences. And they're equally likely. So what is the likelihood of those sequences? So the typical probability then, p bar, would be, so if we have n times 0, if we have 0 that was generated n times p, and we have 1 that is generated 1 minus p, 1 n times 1 minus p. Okay, let me write it first and explain. So if a typical sequence has n times p zeros and n times 1 minus p ones, right? And they independently generated those bits. So the probability for this binary string to occur is equal to probability that you have 0, and that happens np times, and probability that you have 1, and that happens n1 minus p, n times 1 minus p times. So what is this value? So the best way to calculate this is to take the log of this. So if you take the log 2 of this typical probability, so that is equal to, and I have np log p plus n1 minus p log of 1 minus p. By the way, do correct me if I write something that in your view, yes, please.
Don't you have to also multiply this by
We have a microphone.
Sorry?
Don't you also have to multiply this by?
Do you want to see just show the rest of the cards from here?
Oh, yeah, no, the question is, I can repeat the question. Do I have to multiply it by a binary coefficient? Yes. If I were to be asking for the probability, what is the probability that I have this value, this number of zeros and this number of ones? Yes, but I'm just asking what is the probability of one particular sequence in this set. Okay, so you're right. So the question is very good, because the question is, okay, so you have many, many, many points that have this property here. And so the question is, if I were to evaluate the probability that I end up with a binary string in this set, I would have to multiply this probability, the probability of individual appearance of individual sequence, by the number of sequences I have in this set. But this is only the probability of one of them, okay? And as you can see, it doesn't matter whether, as long as the number of zeros and ones is the same, the probability of each binary string here, and we assume we sort of, we fix the numbers of zeros and ones to the averages. So the probability of the single one will be this one. So that equals to n. Or I can write it as minus n, and I can write this part here as minus p log p minus 1 minus p log 1 minus p. And this expression, I'm sure you know, this is a Shannon's entropy. Okay. So therefore, so therefore, if therefore the value of p, if you want to get it from here, so let me write it here. So this typical p then is equal to 2 minus n Shannon's entropy. So that means like the number, so the total number of binary strings of length n is 2 to the n, but the typical set has only 2 to the n multiplied by Shannon's entropy, number of strings. And they are all equally likely. So that means that, so that means like generate long string and of length n. If n is sufficiently large, almost certainly you will end up in the typical set. When I said almost certainly, what does it mean? Can I quantify this? So that means, like, this goes back to your question. So, you know, what is actually, if there is a small probability, of course, that, say, called epsilon, then the string such generated will be outside this set. And what is this probability? So there are many, the so-called concentration inequalities. Some due to Chernoff, and the other one to a person called Hoffendijk, I think. If I can never remember his name of the guy. You have to look up this. I think it's a Finnish or a Dutch name. And you've got it. Yes. And so so there's a bound which essentially goes this way. It says that in this particular case, the probability that, well, if you want to write it more precisely, sum over I, xi is this random variable, either 0 or 1 divided by n. So that means like the average number of ones in the system, okay, minus the typical value that you expect, sort of x. So the probability that this is different by epsilon. So in this case, what I'm saying is that you have this average value of average number of ones. So the probability as we go along with n that this is greater than some small epsilon is bounded by 2e to minus 2n epsilon squared. So this, well, if I were to write it precisely, so this, I think it's so good that I don't want to write here. Well, okay. So you know what I mean. This should go here. So this is actually the very interesting bound, which says, look, what it says is that this probability that we just sort of end up outside this typical bound goes exponentially small with n. So almost certainly if you have large n, you end up there. And there in this typical set, all binary strings are of the same probability. They appear with the same probability. I'm not going to use this, but I say this kind of trick is used when you go from the finite to asymptotic cases, sometimes also in crypto, even though in crypto we prefer to use the mean entropy if you want to be on a safe side. But sometimes in asymptotic cases, we switch to Shannon's entropies for a good reason. But I'm going to use this. What's the name of the guy again? Can you come and write it down for me? Thank you for maybe here. No, he's not the happy guy. The happy guy. Happy. Thank you. Yes. So he came up with several of those bands, but this one I'm going to use later. Okay, so this is like, let me just summarize. Where are we now? What am I talking about? So at the moment, we had sort of an introduction about Bill and his technology. And remember, my objective at the end of this lecture is to be able to purchase device from Bill, given a certain type of construction and design and correlations that I can detect. I'm nowhere near yet in my lecture. For now, I was telling you that I certainly wouldn't be caring about whether bits are equally distributed, whether this device generates zeros and ones with the same probability. I don't care about this. All this was just to tell you that there are techniques which take something that is not maybe so random and make it more random. Usually the price to pay, like in case of the von Neumann extractor, is just we have to drop some data. So we take strings and make them shorter. In this case, it's, there's still the string of like that, but you can actually do the relabeling of those and make this set is smaller, so you can make it actually shorter. That doesn't really matter though. So let me then now at this point move to much closer to what Bill is going to do, to the design of the boxes, and then later, especially how do you pronounce this name? Oh yeah, he's Finnish, yes. Anyone from Finland here? Call him Mr. H. So the age inequality, this one I will use later. So this will stay, or I can write it again later on. It's very useful. I mean, it's if you want to remember one, this one is super useful. For example, it's used all the time in all opinion polls. For example, if you just want to know whether someone will vote for party A or for party B. And so the question is, how many people you have to take as your sample to get a good estimate. So you can use this, just literally, you can use this, put a 0 for one party, 1 for the other party, and that gives you the error estimate. So it's just, you'll be surprised how small, even if you have a huge population of the millions of people, sometimes, having like a few hundreds is more than enough to give you, as long as you sample them randomly from the population, that gives you a pretty good estimate. So this inequality is worth knowing no matter what. Whatever you do, there are a few things we remember in life. Maybe one of them is to remember the inequality, the name you cannot pronounce. Okay, so to the build design. The coffee time is what? 3. Sorry? 3. Oh, no, it's 3:30, I know. Or is it?
We broke it.
So half an hour. Okay. Intro to Bill's design in half an hour. Right. So so now has anyone talked about Bell inequalities? Yes. So
You talked about it.
I did, but not in great detail. It was a propaganda talk, just a few slides. And
I did a little bit, not propaganda.
Oh, you did?
I flashed the proof of the original and the CHSH version.
Did you brainwash into S = 4?
No, I showed
Okay. Fine, good, great. So let me, I will not then go into details. I'll just maybe rephrase few things so that it fits my narrative, but I assume that you know things, but do ask questions, of course, if not. So now about two boxes. So one modern take on Bell inequalities is that you have those two boxes. This time I put them in a vertical way, but later I'll just rotate by 90 degrees because it will be just easier. So those two boxes with input X, output A, another box with input Y, output B. And those two boxes cannot just communicate when the process of data generated starts. So if you are given such two boxes, of course, you know, the most general input-output scenario, so we are still operating in the same scenario that I just outlined, that we have input that is binary, output that is binary, and if you want to describe the whole setup, again, under IID assumptions here, you can say that this is all described by probability that I get output AB condition on inputs XY. So this is actually a set of conditional probabilities. I like, and many people like to write it as a matrix. So you write it as a matrix where you put Y equals 0 here, Y equal 1, X equals 0, X equal 1, and you have all those entries here. So each sub-matrix is a probability distribution of outcomes A and B. So for example, if input is X equals 0, Y equals 0, so this gives you the probability distribution of outputs A and B. So in fact, you have like 4 different probability distribution, each for any particular input. And the interesting question is, no, we have, of course, this is a probability distribution, so there are some usual mathematical assumptions here that with each probability is normalized and all those numbers are positive, or at least non-negative. But otherwise, what is the form of this probability distribution of these things P depends on the underlying physics. And the whole sort of a story is to show that a kind of physics Einstein-like, this local realist, that boxes react locally to well-defined instructions. So if they show any correlations, those correlations are due to the fact that they were pre-programmed to do so. So they got a set of instructions well in advance, because once the experiment starts, the boxes cannot communicate. So any correlated behavior is due to the fact that whoever designed the boxes, Bill, of course, at the very beginning pre-programmed them in a certain way. So here is the first attempt. Let's look at the two boxes when Bill knows exactly what kind of outcomes will I see. So this, or at least sort of can make predictions. And so this is the case, certainly, when boxes evaluate Boolean functions. So that is the only actually way. So if you think about this, whatever, you know, it could be something super complicated inside this device. But from your perspective, it's just input-output device, right? So it takes input X, generates output A. And it is one of the 4 Boolean functions in this case. So this is going to produce in A of X, and this is a B of X, B of Y. So if so there are 4 Boolean functions, constant at 0, constant at 1, identity, negation. So in fact, there are only 16 different scenarios here. And So what Bill can do is to feed instructions to those devices, which Boolean function is supposed to be evaluated. So that's, so you may think that those instructions lambda may have this form, like 0, 1, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, and so on. So what it means, so this is like a quadruplet, A0, A1, B0, B1. So those are the instructions. Say this is the value of B0, sorry, A0, and this is the value of A1. So that means the box on the left is evaluating function that is identity, or otherwise, you know, if input is 0, output 0. If input is 1, output 1. And the same for the second box. And here again, so the values of what should be generated are specified. So this is a set of instructions that Bill prepared for the box. So the box truly, once you have the value of, once you know these instructions, you know exactly how the box is going to work. And so this is kind of more or less Einstein's dream. Now, traditionally, physicists didn't use zeros and ones, and so they looked at, in fact, instead of a of x, the old-fashioned notation would be a sub x, which is equal to minus 1 a of x. So in other words, for 0, substitute 1. For 1, substitute minus 1, right? So instead of, you change the label. So instead of writing this as 0, 1, 0, 1, you would just be writing this 1 minus 1, 1 minus 1. Doesn't really matter, except that certain calculations are easier. When 0 appears, 0 cancels so many things. So sometimes you want to play Trevor tricks with random variables. So it's easier to do many calculations with plus 1 and minus 1. Not that it matters that much, but it is certainly the case. So then the question is, if this is the case, can we somehow figure this out in a simple way? If such instructions are fed into the boxes, can we know this? Can we know that those boxes reply in a certain way? So the answer is yes, we can. And so this is going to be the crucial point, of course. And so the physicist then said, okay, using this notation for, so let me write it again. If I, instead of AX, now I switch into A sub X, and this is equal to plus or minus 1. And instead of BY, I switch into B sub Y, and this is equal to plus or minus 1. So the physicists say, well, look, for example, at the following quantity, call it S, and I write it this way: A sub 0, B0 plus B1 plus A sub 1, B0 minus B1. Okay? So just look at it. So that's for any quadruple of this time, you can assign, using sort of this notation, you can assign the value of S. And of course, here, A0, B0, B1, A1 have values, either plus 1 or minus 1, according to things. So this set of instructions will have a well-defined value of S. What could it be? So B0 and B1 are either the same or different, right? So that means one of those terms has to be equal to 0. So either this one or this one is equal to 0. If B0 is equal to B1, this thing is equal to 0, we only have this term. And if they are different, one is plus 1, the other one is minus 1, then this one is equal to 0, and we only have this one. So we have one of those two terms. And so suppose we just have, they are equal in this case, B0 plus B1 is equal to plus 2 or minus 2. And we have here plus or minus 1. So clearly, we can see that S is equal either to plus or minus 2. There's no other option. So to each of this, we can associate the value plus or minus 2. I don't know what it is, but you can calculate. It's one of the two. So each quadruple would have S equal to plus or minus 2. And if I see many realizations, if I just watch those devices generating numbers, and I observe either I observe AX and BY, I can estimate the average value of S. By the way, I don't have value of S in any single experiment, because in this experiment, I may not know what the instructions are. However, I could see the output 1, and I could see the, so in other words, maybe it's better to say it this way. At any single run of those two devices, I only get two numbers, one from one device, the other one from the other device. So there are then 4 possible pairs, and I can then look how frequently those pairs appear. So in other words, if I want to take the average of this S, from this follows that the observed average would be something like the average of A0, B0 plus the average of A0, B1 plus the average of A1, B0 minus the average of A1, B1. So I can see, I can estimate the average value of S. And clearly, the average value of S is somewhere between 2 and minus 2. So this is known as the CHSH inequality. So that means that if I can do this test, the CHSH test, what it means is that as long as the S is within this range, then the devices could be pre-programmed. There could be a set of instructions. There could be something that is there, and therefore, so Bill clearly, Bill managed to pre-program those devices. The devices may not, but they may respond. So if you look at the sort of like the worst case scenario, you say, aha, with this figure of merit between -2 and 2, I better just give the devices back to Bill and ask for my money back. However, and here's an interesting thing, however, if this value of S goes outside this range, and it can, then the story becomes interesting. And I think maybe that would be a good time to take a break, and I'll just continue. Okay? So, is it good for coffee now?
I think coffee should be 3:30, so I think it's a very good time to say.
Yeah. So sorry?
Half an hour break?
Yeah, half an hour.
Ish.
Half an hour-ish, yes. By the time I'll try to learn how to pronounce this name. Yeah, so half an hour.